An AI agent can receive one instruction, work for an hour, use several tools, inspect dozens of files, and complete a fairly complicated task. That sounds efficient. Then you open the usage page and discover that the agent processed several million tokens. How did one request become several million tokens? The answer is repetition. An AI agent doesn't normally read your project once and then keep everything stored permanently inside its mind. Every time the agent takes another step, much of the relevant context may be sent to the model again. The system instructions are sent again. The available tools are described again. Important project files may be included again. The conversation history is included again. Then the agent adds the result of its latest tool call and asks the model what to do next. If that process happens 50, 100, or 200 times, the same large block of text may be processed repeatedly. And this is where prompt caching becomes extremely important. Prompt caching allows a model provider to recognize that a large part of the prompt has already been processed. Instead of performing the same work again from the beginning, it can reuse some of the previous computation. The agent still receives the information it needs, but the repeated portion may become much cheaper and often faster to process. So let's talk about how that actually works, why it matters so much for agents, and why simply turning on a cache does not automatically solve every cost problem. Why agents repeat so much information? Let's begin with a normal chatbot conversation. You send a question. The model receives your message, generates an answer, and the request ends. You might continue the conversation, but there are probably only a few messages in the history. The total prompt may still be fairly small. An AI agent works differently. Suppose you ask a coding agent, "Open this application, find the login problem, fix it, run the tests, and make sure you haven't broken anything else." The agent may start by inspecting the project structure. Then it reads the authentication files. Then it examines the database configuration. Then it runs the application. Then it reads an error. Then it searches for where that error is generated. Then it edits one file. Then it runs a test. The test fails. So it reads another file, edits the code again, and repeats the test. Each of those actions may involve another model request. The model is not necessarily running continuously during the entire task. It may operate through a loop. The application sends context to the model. The model decides which tool to use. The tool runs. The result is added to the context. Then the application calls the model again. That loop may continue dozens or hundreds of times. Now, what does the application send during each call? Usually, it includes a system prompt describing how the agent should behave. It may include thousands of tokens explaining rules, coding standards, safety restrictions, and output formats. It also includes descriptions of the tools. One tool may read files. Another may edit files. Another may run terminal commands. Another may search the internet. Every tool description can include its name, purpose, input format, and required parameters. A sophisticated agent can have many tools, so the combined tool definitions may already occupy thousands of tokens. Then the application includes project information. That could contain a repository map, coding guidelines, important source files, documentation, and the agent's current plan. Finally, it includes the conversation and tool history. So before the model even sees the latest test result, it may need to process a large amount of information that it has already seen during earlier steps. This repeated input is where agent costs can grow surprisingly quickly. A simple agent cost example. Imagine an agent has a stable prompt containing 60,000 tokens. That stable section includes the system instructions, tool descriptions, repository information, and several important files. Now imagine that the agent runs for 100 steps. At every step, it receives that same 60,000 token foundation, plus a smaller amount of new information. Without caching, the model could process that 60,000 token block 100 separate times. That is 6 million input tokens before counting the changing conversation history, tool results, or generated output. And 60,000 tokens is not especially large for a serious coding agent. A large repository, legal document collection, or research project can easily require far more. This is why an agent can become expensive even when its visible answers are not particularly long. Most of the cost may not come from the final response you read. It may come from repeatedly processing the hidden instructions and context needed to keep the agent working. Prompt caching is designed to reduce that repeated work. What prompt caching actually stores? The word cache is used for many different things in computing. Your browser caches images, so it does not have to download them again. A website may cache database results, so it does not have to repeat the same query. An application may cache a completed AI response and return it when someone asks the exact same question. Prompt caching is different from simply saving a previous answer. The model provider is usually caching part of the computation created while processing the prompt. To understand that, we need to look briefly at what happens when a model reads text. The prompt is divided into tokens. Those tokens move through the model's layers. During attention, the model creates internal representations often described using keys and values. These representations allow later tokens to attend to the information that appeared earlier in the prompt. Processing a long prompt produces a large amount of internal state. Normally, when you make a new API request, the model has to recreate that state by processing the prompt again. But if the beginning of the new prompt is exactly the same as the beginning of a previous prompt, the provider may be able to reuse the state it already calculated. Instead of recomputing the entire shared prefix, it loads the cached representation and begins processing from the point where the new content starts. The model still has access to the earlier information. It simply avoids repeating some of the expensive work needed to process it. That is the main idea behind prompt caching. Why the beginning of the prompt matters. Prompt caches commonly work on a prefix. A prefix is the beginning portion of the prompt. Suppose the first request looks like this: system instructions, tool descriptions, project documentation, important source files, user request. The second request might contain the same system instructions, the same tool descriptions, the same project documentation, the same important source files, the original request, the agent's previous action, the latest tool result. Because the beginning remains identical, the provider may reuse the computation for that shared portion. Only the new section needs to be processed normally. This is why prompt order matters. The stable information should generally appear near the beginning. The frequently changing information should appear later. Imagine putting the current date, a random request identifier, or a changing status message at the very beginning of the prompt. Even though the rest of the prompt remains the same, that early difference may prevent the provider from matching the cached prefix beyond that point. A tiny change near the beginning can invalidate a very large section after it. So prompt caching is not only a feature you enable. It also affects how you design the prompt. An analogy: the briefing folder. Think of an agent as an employee receiving a briefing folder before every task. The folder contains 200 pages of company rules, project documentation, tool instructions, and reference material. After reading all 200 pages, the employee performs one action. Then you ask for another action, but first, you hand over the same 200-page folder and require the employee to reread it. Then you do it again and again. By the 20th step, most of the employee's time has been spent rereading information that has not changed. Prompt caching is like allowing the employee to say, "I already studied the first 190 pages. Just show me what changed." The information is still available. The employee is not ignoring the earlier material. But the repeated review becomes far more efficient. That is why caching works especially well for agents. Agents often have a large, stable foundation, followed by a relatively small amount of new information on each step. Cache writes and cache hits. Some providers expose prompt caching using two basic events. The first is a cache write. This happens when the model processes a prompt section for the first time and stores the reusable representation. A cache write may cost the same as normal input processing, or sometimes slightly more, because the provider also needs to store the result. The second event is a cache hit or cache read. This happens when a future request begins with the same cached content. Cache read tokens are often priced much lower than normal input tokens. The exact discount depends on the provider and model. Some providers charge a fraction of the normal input rate for cached tokens. Others apply automatic discounts when a matching prefix is detected. So the first request may not be cheaper. The savings appear when the same prefix is reused many times. This is important. If a large prompt is used only once, caching may offer little benefit. If that prompt is used 100 times during an agent run, the savings can be substantial. What a cache hit does not mean. A cache hit does not mean the model has permanently memorized your project. It also does not mean the information has been added to the model's training data. The cached representation normally exists for a limited period and under specific conditions. It may be connected to a particular model, account, project, or API provider. After the cache expires, the prompt may need to be processed again. The cache may also disappear if the provider changes the model version or clears stored data. So prompt caching should not be treated as permanent memory. It is a temporary optimization. The model still needs the prompt content to be logically present in the request. The provider is simply avoiding some of the repeated computation. Prompt caching is not context memory. This distinction causes a lot of confusion. A large context window tells you how much information the model can consider during one request. Prompt caching tells you whether repeated parts of that context can be processed more cheaply. These are different features. A model may support a 1 million token context window without offering a useful caching discount. In that case, you can send an enormous prompt, but processing it repeatedly could become very expensive. Another model may have a smaller context window but excellent prompt caching. For a long-running agent that repeatedly uses the same 100,000 tokens, the second model could be more economical. Prompt caching also isn't the same as conversational memory. An application may save facts about you in a database and insert them into future conversations. That is memory at the application level. Prompt caching does not decide what information should be remembered. It only makes repeated input cheaper to process when the same information appears again. And it is not the same as retrieval augmented generation, or RAG. A retrieval system searches a collection and selects relevant documents for the current request. Prompt caching does not search or choose documents. The two can work together. Retrieval decides which information should enter the prompt. Caching reduces the cost of repeatedly processing stable information that remains in that prompt. Why exact matching matters? Most prompt caching systems require the repeated section to match exactly or almost exactly according to the provider's implementation. That means small formatting changes can matter. Changing one space may or may not affect the cache, depending on how tokenization and matching are handled. Changing the order of tools almost certainly can. Adding a timestamp near the beginning can. Generating tool definitions in a different order can. Changing a file's line-ending format can. Including a random identifier can. Even when the information is logically identical, the token sequence may be different. From the caching system's point of view, those are two different prefixes. This is why deterministic prompt construction matters. If your application loads 30 tool definitions from an unordered collection and produces a different order on each request, it may accidentally destroy the cache. If it sends repository files in a different order each time, the same thing can happen. If it rebuilds a system prompt using changing values, the stable prefix may stop being stable. A cache-friendly agent needs consistency. Designing a cache-friendly agent prompt. A well-designed agent prompt can be separated into layers. At the beginning, place the information that changes least often. That might include the main system instructions. After that, include stable tool descriptions. Then include long-lived project rules or documentation. Then include repository content that is likely to remain unchanged during the current run. After the stable material, add the dynamic section. That could contain the current user request, the agent's plan, recent tool results, and the newest conversation turns. The idea is not to make the entire prompt static. An agent must receive new information. The goal is to create the longest practical stable prefix. For example, suppose an agent is working on a software repository. The system instructions may remain unchanged for months. The tool descriptions may remain unchanged for the entire application version. The repository guide may remain unchanged for the whole task. Some source files may remain unchanged until the agent edits them. The command output changes every step. So you place the truly stable sections first and the changing terminal output later. When a source file changes, the cache may remain valid up to the point before that file appears. Everything after the changed section may need to be processed again. That is another reason to think carefully about ordering. Files that change frequently may belong closer to the end. Files that rarely change may belong earlier. The hidden importance of tool definitions. Tool definitions can consume far more tokens than people expect. A simple tool may have a short description and 2 parameters. But a complex agent platform may expose dozens of tools, each with detailed instructions and large input schemas. The model may receive this complete tool catalog on every step. If the definitions occupy 15,000 tokens and the agent takes 200 steps, repeatedly processing them at the full input price becomes wasteful. Fortunately, tool definitions are often ideal for caching. They usually remain identical throughout the session. Place them consistently near the beginning, and a large percentage of their processing cost may become cacheable. However, some agent systems dynamically enable and disable tools. When the available tool list changes, the prompt prefix changes too. That does not mean dynamic tools are always a bad idea. Removing unnecessary tools can improve the model's decisions and reduce prompt size. But there is a trade-off. A smaller, changing prompt may lose some cache reuse, while a larger, stable tool catalog may achieve more cache hits. The right design depends on how many tools exist, how often they change, and how frequently the agent calls the model. Repository caching for coding agents. Coding agents are one of the clearest use cases. Suppose an agent needs to understand a large codebase. The application may provide a repository map showing directories, file names, classes, and functions. It may also include architecture documents, package files, and instructions, such as use TypeScript. Do not modify generated files. Run these tests before finishing. Follow this formatting standard. These instructions remain relevant throughout the task. Without caching, the model may repeatedly process all of them during every tool loop. With caching, that stable repository foundation can become much cheaper after the first call. But the codebase is not completely static. As the agent edits files, some content changes. A good agent system may keep the stable project map and guidelines at the beginning, then place actively edited files and recent diffs later in the prompt. This allows the stable portion to continue hitting the cache even while the work evolves. Another approach is to cache a broad repository summary and retrieve only the currently relevant files. That combines 3 techniques: a stable cached foundation, targeted retrieval, a dynamic working section. Together, these can dramatically reduce the amount of full-price input the model processes. Why caching can improve speed. Caching is primarily discussed as a cost-saving feature, but it can also reduce latency. When a model receives a long, uncached prompt, it needs to perform a prefill operation. During prefill, the model processes the existing input tokens and builds the internal attention state needed before generating an answer. With a very long prompt, prefill can take noticeable time. The model may not begin generating visible output until the prompt has been processed. If most of that prompt is cached, the provider can reuse earlier computation. That may reduce the time before the first generated token appears. For an interactive chatbot, a small improvement may be convenient. For an agent making hundreds of sequential calls, the time saved at every step can add up. If each step becomes 1 or 2 seconds faster, a long agent run may finish several minutes earlier. That said, the exact speed improvement depends on the provider. The cache still needs to be loaded. New tokens still need to be processed. Output still needs to be generated. Tool execution may take longer than the model call itself. So caching does not guarantee that an agent becomes instantly fast. It mainly reduces one particular source of repeated work. What prompt caching does not make cheaper? Prompt caching normally reduces the cost of repeated input tokens. It does not eliminate output token costs. If an agent generates 200,000 tokens while reasoning, writing code, and explaining every action, you may still pay for those output tokens at the normal rate. Caching also does not make new tool results free. A fresh terminal log has not been seen before. A newly downloaded web page has not been cached as part of the earlier prefix. A modified file has changed. That dynamic content still requires normal processing. And caching cannot fix an agent that wastes steps. Suppose an agent repeatedly runs the same failing command, rereads the same error, and makes no meaningful progress. Cached input may reduce the cost of each loop, but the agent is still wasting time and generating unnecessary output. Efficiency has several layers. Prompt caching reduces repeated input computation. Better planning reduces the number of agent steps. Good retrieval reduces irrelevant context. Concise tool results reduce dynamic input. Output controls reduce unnecessary generation. You get the best results when these techniques are combined. When caching produces little benefit, prompt caching is not useful in every situation. If each request is completely different, there may be little stable content to reuse. A simple question answering service with short independent prompts may not benefit much. An agent that uses only a small system prompt may save very little because the repeated prefix is already inexpensive. Caching may also be less valuable when the prompt changes near the beginning on every call. Suppose the application begins each request with current time, unique request ID, current user status. Then it includes the stable instructions. Because the beginning changes, the cache may fail to match the large section that follows. You could redesign the prompt by changing metadata later, assuming it does not need to appear earlier for another reason. Cache duration also matters. Some caches remain available for only a few minutes. Others can last longer. If an agent pauses for several hours between steps, the earlier cache entry may expire. A cache designed for rapid agent loops may not help a workflow that returns once per day. Automatic and explicit caching. Different providers expose caching in different ways. Some use automatic prompt caching. You send requests normally, and the provider detects repeated prefixes behind the scenes. The billing report may show how many input tokens were served from cache. Other providers require explicit cache controls. You may mark specific sections as cacheable or create a separate cached content object. Some systems allow you to choose a cache lifetime. Some require a minimum number of tokens before caching begins. Some only cache at certain token boundaries. Some charge separately for writing and storing the cached data. This means two APIs offering prompt caching may behave quite differently. When comparing providers, you should ask, how large must the prompt be before it can be cached? Does the cache happen automatically? What exactly must match? How long does it remain active? What is the cache write price? What is the cache read price? Does the cache work across separate sessions? Is it limited to one model version? Can several users in the same organization reuse it? And how does the provider report cache hits? Those details can have a bigger effect on agent economics than the normal input price alone. Why the cheapest input price may not win. Suppose Model A charges less for normal input tokens. Model B has a higher normal input price, but offers a much larger discount for cached tokens. For a single short request, Model A may be cheaper. For a 150-step agent run that repeatedly uses the same 100,000 token prefix, Model B could become much cheaper overall. This is why normal token pricing does not tell the complete story for agents. You need to consider the workload. How many model calls will the agent make? How large is the repeated prefix? How much content changes between steps? How effective is the provider's cache? How much output will the model generate? How often will the cache expire? The best model price for chat may not be the best model price for autonomous work. Agent economics are shaped by repetition, caching, and long context windows. Long context windows make prompt caching even more important. A model may be capable of processing hundreds of thousands or even a million tokens. That allows an agent to receive a large software repository, a collection of legal documents, or a long research archive. But context capacity and context affordability are not the same thing. Being allowed to send 1 million tokens does not mean you want to pay the full input cost 100 times. Without caching, long context can become financially impractical for repeated agent loops. With caching, the model can repeatedly work against a large stable knowledge base while only the changing section is processed at the normal price. This does not make 1 million token prompts cheap in every case. The first processing pass can still be expensive. Cache storage may cost money. Changes in the early context may invalidate large sections. But caching can turn long context from something used occasionally into something practical for persistent workflows. Security and privacy. Whenever cached data is involved, privacy questions naturally appear. Is the cache shared with other customers? Can another user access the cached representation? Does the provider retain it after the request? The answer depends on the platform's policies and technical design. In a properly isolated API service, one customer should not be able to access another customer's cached prompt. Cache entries are generally scoped to an account, organization, project, or another isolated boundary. But you should not assume that all providers use identical retention rules. For sensitive code, legal records, medical information, or internal company data, the organization should review the provider's data handling policy. Prompt caching changes the computation strategy. It does not remove the need to understand where data is being processed and how long it may be retained. For local models, caching can happen entirely on your own hardware. A local inference engine may preserve the model's internal state between turns instead of rebuilding it. This improves speed and avoids sending the data to an external provider. But local caching is limited by available memory. A large key-value cache can consume many gigabytes, especially with long contexts and multiple simultaneous agents. So even locally, caching has a storage cost. The future of agent pricing. As AI agents become more common, prompt caching may become one of the most important parts of model pricing. Traditional chatbot pricing focuses on the price per million input and output tokens. Agent workloads introduce additional questions. How much of the input is repeated? How much can be cached? How long does the agent run? How many times does it revisit the same project? An agent working on a codebase for an entire week may repeatedly use the same architecture guide, repository map, and tool definitions. A research agent may repeatedly reference the same collection of papers. A customer support agent may use the same policy documents for thousands of conversations. A legal agent may analyze many cases using the same contract templates and regulations. In each situation, the provider that processes repeated context efficiently may have a major cost advantage. We may also see agent platforms become smarter about managing caches. They could automatically detect stable prompt sections. They could separate rarely changing context from frequently changing context. They could reorder content to maximize prefix reuse. They could maintain several caches for different projects or tasks. And they could decide when rebuilding a cache is worthwhile. The user may never need to manage this manually. But underneath the interface, caching could determine whether an agent costs a few cents, a few dollars, or far more. Closing. So, why does prompt caching make AI agents much cheaper? Because agents repeat themselves. Not necessarily in their visible answers, but in the information they send back to the model during every step. System instructions are repeated. Tool descriptions are repeated. Project documentation is repeated. Repository information is repeated. Conversation history is repeated. Without caching, the model may process that entire foundation from the beginning every time. Prompt caching allows the provider to reuse the internal computation for the stable beginning of the prompt. The first request creates the reusable state. Later requests match the same prefix. The cached section is processed at a lower cost and often with lower latency. But the system only works well when the prompt is designed for it. Stable information should appear early. Dynamic information should appear later. Tool ordering should remain consistent. Random values and timestamps should not unnecessarily break the prefix. And developers still need to control output length, tool results, and the number of agent steps. Prompt caching does not make intelligence free. It does something more practical. It stops the agent from paying full price to reread the same briefing folder every few seconds. And for agents that work through dozens or hundreds of steps, that one change can completely alter the economics of the task.